Okay, hello everyone. Welcome to the last episode of my walkthrough of the big book, New Kind of Science, which will be 20 years old on May 14th. And I've been going through the 12 chapters of this book over the last 12 weeks. Chapter 12 is the longest, the crowning chapter of the book, Principles of Computational Equivalence. I got through about half of it last week. This week, I will go through the second half of that chapter, and then I will talk about a few extra pieces associated with the book and some extra parts of the book beyond the main chapters. All right, well, so just to give an outline here, chapter 12, Principle of Computational Equivalence, the earlier parts of the chapter have talked about the concept of computational equivalence, the idea that programs, as soon as the behavior of a program is not obviously simple, it will tend to be something that corresponds to a computation that is as sophisticated as anything. That idea, the basic implications of that idea, and the kind of evidence for that idea, and the implications particularly for concepts like undecidability, which is kind of like an infinite time version of computational irreducibility. All right, so let's launch into what we can see here. So chapter 12, the last chapter in the book. These are the sections. We went through some of these last time. Last time we had finished with undecidability and intractability. That leaves us this big section, implications for mathematics and its foundations, and then intelligence of the universe, implications for technology and historical perspectives. So let's jump into implications for mathematics and its foundations. So the thing that I talk about is that one of the points of the book is that one can go from simple programs to complicated behavior that is like what's seen in nature. But another kind of very core example of going from something simple, a simple specification, to complicated output is mathematics, where one imagines, at least in the traditional view of mathematics that's existed for the last century or so, that one is sort of starting from axioms, and then one is building up sort of all the true theorems that one cares about of the mathematics from those axioms. So one thing that I did, and I've used these pages so many times in the NKS book, was I put on 2 pages just the standard axiom systems of mathematics. In fact, it even goes overboard. It talks about some sort of alternate axiom systems for mathematics. The real sort of takeaway from these pages is all the raw material, the seeds for all the stuff we do in mathematics. The axiomatic seeds are tiny. So for example, here, this whole section at the top is axioms for logic. We'll talk more about axioms for logic a bit later. Down here, we've got that's propositional logic, just ands and ors and nots and nands and so on. This is predicate logic for all there exists. This is the section, this is arithmetic. This is the standard axioms of Peano arithmetic. This is including things like the a plus 0 is equal to 0 to a and so on. The only tricky axiom, which is really an axiom schema, it's a thing that's sort of a generator of an infinite number of axioms, is the induction axiom. That if something is true, if it follows that the n plus 1th case follows from the nth case, and there's a base case, then that means it's true for all n. I also have here, and this is sort of a bonus piece to this axioms page, the Robinson axioms for arithmetic. These are a simplified form of arithmetic without the explicit induction axiom. Then I have various kinds of other axiomatic theories like semigroup theory, group theory, several different axiom systems for group theory, and so on, several different axiom systems for commutative group theory. As I say, all the stuff that makes the mathematics we normally do from an axiomatic point of view, its seeds can be sown in a very short amount of space. Down here, ring theory, field theory, real algebra. And I go to a second page, and here we've got the axioms for plane geometry. These are actually Hilbert's axioms for plane geometry with these operators like the ternary operator between, D is between E and F and so on. Then we've got elementary category theory, And then down here, we've got set theory. And even below here, we have some additional axioms for topology and real analysis. Now, these axiomatic systems are, in a sense, they're just abstract rules. They just say block dot A equals block, where block and A can be anything, and the dot is just a thing that has those properties. But when we think about these axiom systems and we think about connecting with mathematics, we also have this kind of table of what things of what our interpretation of these kinds of constructs is. But okay, so the idea here is the mathematics that we are used to can be seeded from these very small axioms. Okay, then what do we do when we actually make mathematics? Well, there's another picture I've used many times. This is a picture that shows the way that you use axioms up here to prove a theorem. So what this is saying is, these are axioms. In fact, they're axioms for Boolean algebra. There are 5 axioms here that say things like A NAND B is the same as A NAND B NAND B. So then what we're going to do over here is we're going to try and prove the theorem P NAND Q is equal to Q NAND P. And the whole point is this is a path from P NAND Q using axioms, using transformations that we're assuming are correct, and going from P NAND Q to Q NAND P. And so this is a proof. And this shows how you take, like this is saying, take the Q NAND Q and make that be, use element 2 there. So that means the A is Q NAND Q, and then fill that in to this output, and then that turns into this big long thing here. And the whole point is that we can find a path that goes from P NAND Q to Q NAND P, and that therefore establishes that that's true if we're assuming that these axioms are true. And so this is part of sort of a minimal meta-modeling of mathematics. What is the raw material? What is the underlying kind of structure of rules that we can use to get mathematics? And this is part of that story. Okay, now we go even more minimal here. We say, forget having all those symbols, and later on, well, we'll talk a little bit more perhaps about the difference between having those explicit variables and parentheses and all that kind of structure, ultimately tree structure. And we'll say, now let's just replace that with just pure strings and say our axioms are just these string transformation rules that say things like a white cell goes to 2 black cells. Then here are the proofs of a few theorems. This theorem says that white, black, white is equal to black, white, black. And this gives us the proof of that theorem as a series of steps. Now, I might say that this section of the book is something that for many years didn't really develop much. And then just in the last few months has had a lot of development. And it's led to this big piece that is about a 200-page piece in its own right that I brought out called The Physicalization of Metamathematics and its Implications for the Foundations of Mathematics. This is a piece that has as its launching point this section of the NKS book, but is then further informed by a lot of things that we've done in our physics project. So, but this idea of a proof as a path that between expressions, that's something that shows up a lot in this physicalization of metamathematics, and something we see here in the NKS book. Okay, so now those are some examples of specific proofs we can do. But what if we ask, given this axiom system, what are all things that are true? Well, then we get our friend a multi-way system. And we say, if we start from white, black, white, these are all the strings that we can get from white, black, white. So for example, the proof that we showed on the previous page, that white, black, white is equivalent to black, white, black, that is one of the paths that leads from here to that state there. And for example, there will be a proof that this white, black, white is equivalent to white, white, black, and that will correspond to some path that we'd have to trace through this picture to go from this initial state to this state here. So this is, in a sense, what we're calling these now are entailment cones. This is sort of the multi-way system that represents kind of all of the true results, all of the theorems, all of the expressions that can be found to be equal to this expression here. Okay, so these are multi-way systems that show, as I say, the analog of long proofs. The basic point here is if you're trying to prove, I don't know, that as a good example, well, this thing here, this string there is equal to black, black. Well, the shortest way you can do that is to go through all these steps and get to black, black here. So what is this about? Well, this is kind of the analog of beginning to get towards Gödel's theorem and beginning to get to the idea, well, maybe we can't really tell you whether there is a finite way to reach this particular result. Maybe the proof could be arbitrarily long. Maybe we can't give an upper bound on how long we'd have to wait, how far we'd have to go through what we now call an entailment cone to get to that particular result. So this is sort of a first example of that phenomenon. This is an example of computational irreducibility applied to what is essentially a mathematical or meta-mathematical structure. I say meta-mathematical because in mathematics, you're typically interested in what's the answer, what theorem is true. In meta-mathematics, you're interested in the whole structure of all possible theorems, the structure of all possible proofs, those kinds of things. Okay, so now we're talking about here, talk about multi-way systems, and the fact that it's important that if you're going to get something where it's not easy to tell whether you can get to a particular answer, there has to be the case that you can both expand the lengths of these strings and contract them. If you were always contracting the length of the string, you could always say, oh, I just reached 0. I know I'm not going to get any further. But if you can expand and contract, you may be wandering around in the wilderness of length 100 strings, not knowing whether eventually the thing will compress down to a length 2 string and get you the result you were looking for. Okay, so let's see. I talk here about the fact that one can, just like in computational irreducibility, there will be particular jump aheads you can make where you sort of cache a particular part of a computational result. You can do the same thing in mathematics by adding certain lemmas, which are additions to the axiom system that say, here's this new axiom system that lets you jump from this one stage in the multi-way system to a quite different stage. Okay, so one of the things about those multi-way systems back there is that they were multi-way systems that represented equivalences between expressions. We're trying to prove something like P NAND Q is equal to Q NAND P. Now, a lot of the way that mathematics is done, and this has developed much more in the recent physicalization of mathematics that we've been doing, but the way mathematics is often done is not to say we're going to go from one expression to another, but rather to say, let's just find all theorems that are true. So let's try and transfer P NAND Q equals Q NAND P and say that's true. That whole thing is true. Not we're going to find the path that gets us from the left-hand side to the right-hand side, but that whole stated theorem is true or isn't for that matter. And so it's a slight reformulation of what we're doing. And I did this in the NKS book of saying, well, let's imagine that we have a setup where we can just say that a single black cell means true. And then we can say that every one of these strings represents a whole theorem, something like P NAND Q equals Q NAND P. Again, this is done in much more detail and better in the recent physicalization of mathematics, but it's the same basic idea. And then we can say, well, now these transformations represent transformations, I call these rules between rules in the physicalization of mathematics. These transformations from one essentially rule to another rule here, or another one equivalence to another equivalence. But anyway, what we're seeing here is these are true results. Anything that can be derived from true is true. So in this system, black, white, white represents a theorem that is true. Okay, so given that, this is asking the question, oh, I didn't actually even remember that I had this in the NKS book. I think I talk about this again in the physicalization of mathematics. This is a tautology. P NAND P is something that we can sort of say is, we know from our interpretation of NAND that means true. And so this picture is an entailment cone that shows true results. These are other things which are true, other tautologies of Boolean algebra, represented in terms of the NAND operator. And it grows very exponentially, and I talk about that here. Okay. So talk here about the fact that in the early 1900s, that's really Hilbert's program, it was believed that sort of if you started off from a reasonable mathematical axiom system, then all the true statements of that area of mathematics could be proved from that axiom system. It's kind of a muddled idea, and we'll talk about why it's muddled. But the thing that made it clear that that wasn't going to work was Gödel's theorem from 1931. And this thing where you say, well, I've got this axiom system, we showed it a few pages ago, that we think represents arithmetic, Boolean algebra, so-called Peano arithmetic. I showed that back when we were talking about different axioms for mathematics. There it is. There's the Peano axioms for arithmetic. There they are. And what Gödel said was, okay, if that's really supposed to represent arithmetic with integers, then is it true that that can really prove all statements that we can make up in terms of integers? Can it either prove or disprove all statements we can make up in terms of integers? Well, said Gödel, what about the statement, this statement is unprovable? Can it prove or disprove that statement? Well, the thing at first is that statement doesn't seem like it's a statement about arithmetic. And Gödel's big achievement was to show that you could essentially compile that statement into a statement about arithmetic. You could write a version of that statement in terms of equations involving integers and things like this. You could compile that into a statement in terms of arithmetic. And then by the structure of that statement, it's sort of paradoxical statement, you can show that you can't then, you can't reach every statement in arithmetic from the axioms of arithmetic. But put a different way, it's really saying that there may be proofs about arithmetic with those axioms that are arbitrarily long, that do not have, where you could say, well, there is a statement out there that could be correct according to those axioms, but there's an arbitrarily long, potentially infinite path that will be needed to reach it. Well, so I talk here about, okay, this is about adding transformations to the rules for a multi-way system and asking the question, okay, so one of the issues is with respect to this kind of interpretation of truth, where you say a single black cell means true and everything derivable from that must be true. So one question is, well, then what's false? Well, here's a very simple thing you could do. You should just say, imagine the negation operation is pure inversion of black to white. Then false is white. And then if the statement black, white, white is true, it's derivable from true here, then white, black, black should be false if negation is indeed exchanging black and white. And so there's sort of a question of, can you, with a particular axiom system here, will you get something which is consistent and or complete in that kind of way? So what I'm now talking about here, I think I have a picture. Let's see, where does it come? Oh, I thought that picture was earlier. Hold on one second here. Hold on a second. I may not know my section well enough. Yeah, let's take a look here. Oh wow, I talk about other things before I get to that. Well, let me jump to this. Yeah, I'm talking about this question about compilation into arithmetic. That's the early thing I'm talking about. But what I'm going to get to afterwards is this question about, well, what theorems can we actually reach? If black is true, what theorems can we reach from black with a particular axiom system here? And so what this is showing is these are possible theorems up at the top here. And this shows how many steps it takes to reach one of those theorems from black, which means true here. So down here, for example, with this axiom system, we're reaching all kinds of theorems here, although some of them take a while to reach. And some of them we're not reaching at all, like we're not reaching the pure white from that black initial thing. So if the black initial thing represents true and negation is black to white, then in this case, we're not reaching white, which is all good. We shouldn't be able to prove false from true. Okay, so now what I ask here, this is kind of the Gödel's theorem page in some sense, is I'm asking the question, given a particular axiom system, do I manage to underprove or overprove or neither theorems in this system? So by underprove, I mean there are theorems that where neither the theorem nor its negation nor the black to white flip of the theorem is ever reached starting off from the single black cell that means true. So that would be what we would call an incomplete axiom system. It doesn't completely reach all possible theorems, assigning them either true or false. The other possibility is that they could be inconsistent. That is, that from true, you could prove both a result, a theorem, and its negation, and the black-white flip around of that thing. So, and the other possibility is that you nail it right in the middle, and it is complete and consistent. So a way to get an indication of that is simply to ask, what fraction of theorems are we going to reach? And so here, for example, we're seeing something where the fraction of theorems we reach is much less than 50%. So that means that we are very incomplete here. There are many theorems we cannot get either true or false for. Now, in other cases here, we're getting this one here, we're getting many more than 50% of theorems. So that's a case where we're inconsistent. We're proving both the theorem and its negation. But in other cases, we're right. We seem to be right on the nose. We're proving exactly 50%. And we can see that we have something which appears, at least to this point, to be complete and consistent. All right. So one of the things that I'm talking about here is sort of Gödel's theorem is all about the case where that happens in arithmetic, where there is incompleteness, where there are theorems that are statements about integers, but we can't reach them from the axioms of arithmetic. Okay, so going back here to where we're talking about, well, could we fix that by just sort of adding axioms to our system? Can we fix an incompleteness or an inconsistency? And the answer is that there are cases in which we can never quite get it. We'll always be missing. We'll never quite be able to fill in the collection of lemmas. There'll be an infinite collection of these things, an infinite collection of patches that we need to make. It's kind of like when you get to kind of computational legal systems, you say, based on the things that could happen in this world that is a computational world, will we ever have exactly what we need in this set of constraints that we're defining on what we think we should allow? And you realize there'll always be these unexpected pieces that will require an infinite collection of patches. And it's the same kind of story here with a sort of infinite collection of additional axioms that we have to add. And okay. So one of the things that I'm asking here is, when can one prove computational irreducibility? When can one prove incompleteness in the sense that there's an arbitrarily long path to reach the theorem? How could one prove that for mathematics, and particularly for arithmetic? And so I say that the main way one can prove such things is to show that a system is universal. That leads to computational irreducibility, undecidability, this whole pile of consequences. So the question then is, what axiom systems in mathematics are universal? And well, I say basic logic is not universal. One can always, in principle, determine the truth of any expression by the finite, if exponentially long, procedure of trying all possible combinations of truth values for the variables that appear in it. You can test the satisfiability of any expression, any Boolean expression, by just saying it's got P, Q, R, and so on. Just see what happens. If P is true, Q is false, R is true, with all possible combinations, and eventually you'll know, is this theorem a tautology? Is it something that's always true or not? It's a very deterministic, finite procedure. Okay, so the question is, apart from There's also pure predicate logic. That's actually Gödel's first big thing Gödel proved. Gödel's completeness theorem, instead of his incompleteness theorem, was the completeness of pure predicate logic with for alls, and there exists, but no actual functions that say what it is for all, and so on. So in any case, then the point that I make here is that apart from these sort of starter cases of Boolean algebra, propositional logic, and pure predicate logic, all other known axiom systems used for real mathematics are known to be universal. And so that's an example of basically something like our principle of computational equivalence. It's saying that even these very simple axiom systems, as soon as you're out of the ones that are sort of very easy to handle, they will end up being things that sort of have arbitrary computational richness and universality. Okay, so let's take Gödel's theorem and arithmetic, which is the particular case that Gödel looked at, the Peano axioms for arithmetic, and at the question of whether they are universal. Okay, so is arithmetic universal? So this is a kind of a pictorial proof or evidence of the universality of arithmetic. So what would it mean if arithmetic was universal? It would mean that, for example, you could write down an equation involving integers, for example, and you could say, if this equation has a solution, then the result of such and such a computation that is encoded in that equation is such and such. If it doesn't, then it's something different. Okay, so what this is doing on this page is it's showing how to compile Rule 30 into a Diophantine equation, into an equation involving integers. And so it's a kind of a messy thing. It goes through something that's kind of like a register machine. Boy, how does this actually work? This is saying, right. It's saying that this is showing how the successive values of the variable x4 as initial width, initial state, number of steps, and evolution. Okay, so what's happening here is we are fixing certain values, and then we're trying to determine by solving the equation what the value of this evolution parameter is, which is going to give us the picture of the cellular automaton. So what we're saying is with initial width 3, that's x1 equals 3, x2 equals 5, x3 equals 4. Now we want to say solve for x4. Okay, big messy equation here, actually solve for all these variables, but in particular solve for x4. Or is there a solution for x4? For what value of x4 is there a solution? Okay, given that solution, we can decode x4 into this bit pattern, and we're essentially showing that the solving of this Diophantine equation is equivalent to the evolution of Rule 110. So that's giving us an indication that these Diophantine equations are equivalent to this problem, this computational problem of the evolution of Rule 110. Rule 110 is known to be universal, and so with a little bit of dotting of I's and crossing of T's, we can show from this that arithmetic is universal. Now, one of the things historically of interest is that Hilbert's 10th problem was this question of whether Diophantine equations, whether you can in general say whether a Diophantine equation has a solution or not. He talked about sort of ordinary Diophantine equations that involve multiplication and addition. This also contains exponentiation. So there are variables like x19 here is in the exponent, and that makes it a slightly richer set of Diophantine equations. And it was a big effort that was finally finished in 1968, I think, to show that even Diophantine equations without exponentials still have the feature that you can use them to compile arithmetic into. They are therefore universal, and therefore it's undecidable in general whether there will be a solution to such an equation. Okay, so one thing I talk about is, okay, so we're claiming that arithmetic is universal. The question is sort of how far away is is universality in how far away is something like undecidability in something like a system with Diophantine equations. It's kind of like asking, okay, it's fine, we can construct a cellular automaton that is computationally universal, but what about a particular cellular automaton like Rule 30 or Rule 110? Is that universal? Where is the frontier of universality in different kinds of systems? For cellular automata, we know the frontier is right at the lowest point, where it's just two colors per cell, nearest neighbors. Okay, we've got Rule 110, it's universal. For Turing machines, it's not at the very, very lowest point. It's not 2 states, 2 colors. It's 3 colors, 2 states. That's already universal. So the question is, for Diophantine equations, for equations involving integers, where is the threshold of universality? It's been a fun question. I've asked lots of distinguished number theorists for about 40 years now, and people have different speculations about how this works. But for the NKS book, what I wanted to do is to get some sort of indication of where the threshold of universality in Diophantine equations might be. And I wanted to get that indication by the same kind of technique that I used for things like cellular automata. You run the evolution, you see what it looks like, you get some sense of, is it complicated, is it not? And the analog of that for Diophantine equations is, given the equation, how complicated is the solution? So these are cases where I could tell that for example, well, what's a good example here? This one here, x squared equals y cubed minus 18 has this first solution. This one here has no solution. And so over here, my favorite collection were x cubed plus y cubed equals z cubed plus or minus a constant. And you can see that in some of these, like the case of 12, even though there is a solution, in the case of 13, there's no solution, and we can show there's no solution. In the case of 12, there is a solution, but it's very big. And that's kind of like saying there is a proof, but it has many, many steps. If we were going to find that solution by just enumerating possibilities, we would have to go a long way to find it. Now, when I wrote the NKS book, there were a few cases where I could prove there wasn't a solution. There are others where I just didn't know. And this one was filled in recently. Took a big effort on many parallel computers to fill it in. And then the case of 42, actually, which was another one which was long-standing, was filled in with a roughly million computer effort from an outfit called Charity Engine that we've been involved with, that is crowdsourced computing resources. So, but the fact that there are those things that far out in the world of Diophantine equations is an indication that even very simple Diophantine equations are likely to engage with computational irreducibility and are likely to show universality. So I talk in this case about what Gödel's theorem means and how important it is. I mentioned here the elaborate proof of Fermat's last theorem have been developed that may make use of at least some axioms that come from fields like set theory that go beyond the normal ones for arithmetic. That came from a conversation that I had with Andrew Wiles actually after that theorem, after he proved that theorem, asking, well, okay, it's, you know, this is a proof. What axioms did you actually use? And it's like, I don't really know, but it's definitely beyond the standard Peano axioms for arithmetic. But I talk quite a bit in the NKS book about the meaning of this axiomatic setup and what really one is doing with axiom systems. And again, I sort of allude to this in the physicalization of metamathematics more recently. My understanding of the philosophy of this has gotten a lot better, but I'll describe a little bit what the NKS book already establishes. It's kind of like you're imagining this unformed thing that is the integers. Now you say, I know various properties of the integers. Can we give enough properties that we put this net down, this mold down that constrains us to have these constraints so that we're talking about the integers and nothing but the integers. And that's what the Peano axioms were supposed to do. They were supposed to be a set of definitions of things that would be integers and nothing but integers. Now, why do you even need to do this? Well, if you we're just dealing with finite questions, you could just run a computer and see what the answer is. But as soon as you're dealing with infinity, you have the potential that you need to be working with things symbolically. You need to be able to say, symbolically, is this theorem true or not, without having to actually work through effectively the cases, even if they're symbolic cases. Well, so what happened, what Gödel's theorem established is that no, you can't make that mold work. You can't make a finite set of axioms which give you sort of just the integers and nothing but the integers. It's an incomplete set of constraints that the Peano axioms give you. And there'll always be things that satisfy the Peano axioms, but they're really wacky and they're not like ordinary integers. So for example, there's non-standard arithmetic where one has things like addition operations that aren't recursive and things like that. So I talk a little bit about that here, and I talk about the summarization of infinity and the relationship between computational infinity and the computational infinity of infinite computational processes and mere and infinite number, and what that means, and the fact that in a sense the number line is a very simple sort of successor computation, but an arbitrary infinite computation is something rather different. Okay, so let's see. Well, I talk about this is a discussion about sort of what mathematics is. And this question of, okay, so one of the basic questions is this: given arithmetic, we know there are undecidable questions. Given essentially any of the standard axiom systems for mathematics, we know there are undecidable questions. But yet mathematicians manage to sort of go to work every day without worrying too much about undecidability. That is, undecidability is a rare phenomenon to rear its head in doing the mathematics that mathematicians ordinarily do. And so that was a question I was very interested in the NKS book. Why is it that undecidability is as comparatively rare in the mathematics that mathematicians do? Now, in our current work on the physicalization of mathematics, I think we have a more complete answer to this question. But when I was working on the NKS book, that was sort of a big question that I wanted to answer. Why is it? How is it the case that the axiom systems that mathematicians work on somehow evade these phenomena of undecidability and so on? And I talk about the fact that some people think of mathematics as being this thing where you can just throw in an arbitrary axiom system and then build a mathematics from it. And that's sort of how mathematics is built, that the seeds are sown and then you grow whatever you want from the seeds that you happen to specify. As I say, in my recent understanding of the physicalization of mathematics, what I've realized is that that isn't really the story, that the story is that in the Rouliad of all possible mathematics is the question of which ones we humans are sort of capable of talking about and which ones are natural to us. That's a subset defined by our characteristics as humans. It isn't sort of an arbitrary collection. But in NKS, I was looking at sort of, so what happens with this sort of arbitrary collection of axioms? Okay, so let's see. Then the question is, okay, so what I'm talking about here is the surprising fact that whereas in doing mathematics, the typical things that people talk about end up being theorems that they can prove that are not undecidable. But in dealing with computational systems, it's very routine to just, as we saw in many places earlier in the book, to just the obvious question you ask ends up that the answer is somehow undecidable or there's computational irreducibility. So why is that? So one of the things I did here was to ask the question, well, could you in fact do these questions involving, let's say, evolution of cellular automata in terms of axiom systems? And the answer is absolutely yes. This is an axiom system for the evolution, well, for statements to be made about the rule 110 cellular automaton. And here, for example, is a statement. This says the evolution, that arrow down means an evolution step. The evolution step applied to a black cell gives a black, and a white cell. And that's the proof of that with this axiom system over here that represents rule 110. So it isn't the case that something like the evolution of rule 110 is off in some other world from axiom systems for mathematics. No, you can write an axiom system for mathematics about Rule 110. So that doesn't really answer the question. It's not that Rule 110 is not an axiomatic system. It is. It's just that somehow the way that the mathematical axiom systems are being chosen or the way they're being used is one that evades undecidability in a way that the typical uses for Rule 110 do not. Okay, so that leads me to the question of, so I'm talking here about this completeness and consistency question. And then I start talking about, somewhere here, I start talking about, okay, what I call operator systems. So let's say you're going to make an axiom system. You can make an axiom system that says something like P dot P equals P. You don't know what dot is. You're just saying that whatever dot might be, I can tell you that P dot P for any P is equal to P. Or P dot Q dot R is equal to P dot Q dot R, the associative rule. Okay, so given those kinds of statements, let's say we have a binary operator, an operator with two arguments, and we make certain statements about it. So we can go the other way around. We can say, let's say we have an operator where this is the multiplication table. So black and black gives black, black and white gives white, and so on. Then we can ask what results are let's see, this is values of expression. So this is, oh, I see. This is given this particular form for an operator, what is P dot Q according to that operator? And the answer is here, P dot Q, there are four cases to consider. P is black, Q is black, over to P is white, Q is white. Each of those has a value according to this form of this operator. Again, there's versions of this in the physicalization of metamathematics that I think are sort of modernized versions of this. Okay. So, given, let me just look forward a little bit. Yes, so I know what I'm doing here. Okay, so given an operator, we can say what a particular expression like P dot Q, what its essentially truth table will be, given this operator. So here we're seeing that P dot Q leads to black, white, white, white. But we see also that Q dot P also leads to black, white, white, white. So we might ask the question, if we just asserted that P dot Q equals Q dot P, would it imply that we have to be talking about this operator here? So the thing I do on the next page is to show that there are, that it's possible to do that, that with these axioms, this one here, A dot A equals A dot B equals B dot A, and this associativity axiom, you are forced to have the only operator that satisfies those axioms is this operator here, at least up to some flip around type symmetry considerations. So that's saying that this axiom system, so when we talked about Gödel's theorem, we talked about the fact that the axioms for Peano arithmetic are not capable of saying we're just talking about the integers and nothing but the integers. But this is a simpler setup where this axiom system can say we're just talking about this operator. The dot has to be just this operator and nothing else. Okay, so that's an example where we can sort of do the completeness thing and show that we've got this axiom system and it nails down the particular operator we're talking about. Okay, so then I asked the question, let's just do a very NKS thing and let's look at all possible axiom systems. This is another page I've used many, many times. Let's look at all possible axiom systems. And let's say we pick the axiom system A dot B equals A. then we can ask what operators are consistent with that axiom system. There might be a size 2 operator, a size 3 operator, and so on. In more sort of in terms of traditional mathematical logic, this is a kind of model theory question. We're asking how many models are there of size 2, 3, etc., consistent with this axiom system. But for our purposes here, what this is saying is, given this axiom system, these are the operators that this axiom system could be talking about, so to speak. Okay, so then the question is, if we just start enumerating axiom systems, the question we can ask ourselves is, well, where are the axiom systems that correspond to the ones that we humans have used for our mathematics? Where do those show up? And the answer is that we're going to go on a hunt for where do they show up, and we've already got some examples. Well, let me show you. This was a big sort of hunt that I did to find the simplest axiom system for Boolean algebra. So I wanted to know what was the let me just pull something up here. What was the very simplest axiom system for Boolean algebra? Now I can show you here the sort of standard textbook axioms for Boolean algebra. I think I have them. No, where do I have them? Oh, the first thing I'm talking about here, before we even get to that. Okay, I'm trying to find the simplest axiom system for Boolean algebra. The standard way to state Boolean algebra is in terms of and, or, not. So the first thing I do here is to say, we can reduce that to just talking about NAND. So these are the 16 possible binary operators with 2 elements here. And what I do here is to show that NAND is enough to reproduce all the other operators. So this is saying that operator 14 can be represented as A NAND A, NAND B, NAND B. These are the so-called functionally complete versions of Boolean algebra. So you can use and or not, you can use implies and not, you can use different combinations, XOR and implies. These all have the property that from these operators, you can construct all the other operators. And NAND in particular is a single operator that allows you to construct all these other operators. And that's obviously important in practical digital electronics because that's what the individual gates on microprocessors are made out of, is NANDs, and they're used to sort of aggregate up all these other different logical operations. Okay, so NAND is enough. So then the question is, well, how can we state the axioms of Boolean algebra in terms of NAND? And the most sort of a basic sort of textbook set of axioms in terms of and or not, we can convert them to NANDs. They're really big and complicated. We can get to various kinds of axiom systems. We get down here with a huge amount of work. People have managed to get to axiom system E after, well, basically 50 years of simplification. They've gotten from B to E, a little bit more than 50 years. And so the question that I had was, let's work up from the bottom. Let's ask the question, if we just start enumerating axiom systems for Boolean algebra, how far do we have to go before we reach something which is an axiom for Boolean algebra? Now, if we hadn't known about NKS, we might have said, that's hopeless. You know, Boolean algebra is this complicated thing, and there's no way you can just start enumerating axiom systems and expect to get to it. But you'd be wrong, because it turns out that axiom there, these two here, are the simplest axiom systems for Boolean algebra. And they are smaller than this axiom. And now, how do you prove that? Well, I talk here about the kind of process of finding those axiom systems for Boolean algebra and using that kind of models method to kind of gradually home in on what the candidates are. And then eventually, ta-da, here's the proof that that axiom system for Boolean algebra that I gave is actually a correct axiom system for Boolean algebra. I printed it in 4-point type. And it spanned 2 pages. And that was a proof found by an automated theorem proving system in 2000. I did this. That's a proof that that minimal axiom system for Boolean algebra is actually an axiom system for Boolean algebra. And in the time since then, nobody's really managed to simplify this proof. It's a very non-human proof. There's a chap actually named Norm McGill who was working on this, unfortunately died at the end of last year, and was actively working on the project of simplifying this proof. So that's another path that hasn't panned out for that. I actually wrote about that proof in a big post that I wrote in 2018 about logic explainability and the future of understanding. That's my minimal axiom system for Boolean algebra. I guess gets called Wolfram axiom these days. I talk about in this post, this is an example of how one page in the NKS book turns into a long post, and you'll see some of the things from the book. That's sort of a pictorial representation of part of the automated proof. And I talk about the significance of it being an automated proof and what kind of thing that means and so on, what that means for kind of understandability. But as far as the NKS book is concerned, the point of this proof was to show there is a very simple axiom system which gives you Boolean algebra. So in that enumeration of axiom systems, we could fill in, put a pin, this is Boolean algebra. Actually, commutative group theory is the winner, well, semi-group theory is the all-time winner for the simplest system, for the axiom system that's used in mathematics that has the simplest axiom. Then it's commutative group theory, then Boolean algebra. Okay, so then here's something that, again, I have redone in the physicalization of mathematics. This is kind of asking the question, if you look at all those possible axiom systems for mathematics, is there something special about the ones that we humans end up using? For example, if we say, here's a possible axiom system, and this is showing which theorems are true for that axiom system. And so this is showing the distribution of true theorems for a given axiom system. Is there something special about the particular ones that we use or not? I have to say this picture was not an easy one to make. This was done using automated theorem proving, and we were filling in, a black cell. Okay, we can prove this theorem. Is it true? Or we can prove that that theorem does not follow from this axiom system. And I really wanted to continue this a little bit. You can see it would have fitted a few more columns in here. But we couldn't go any further because by the time we got to the right-hand edge, the automated theorem proving system had kind of run out of steam, and we were having to do hand proofs. And the person who was working with me started doing some of these hand proofs, and it was taking him like a day to prove or disprove a particular theorem from the axiom we'd given. And in a sense, that's the long arm of computational irreducibility, reaching in and saying, no, there is a proof, but it's really long. There's no reducibility to how to prove or disprove this particular theorem. That's sort of computational irreducibility in your face, so to speak. Okay, so this is, here I'm just showing for the particular case of Boolean algebra, how does this sort of pan out? There's NAND showing what theorems are true for the case of NAND and so on. For some reason, I'm talking here about higher logic with more than two truth values, again, to get a sense of this distribution of what's the distribution of true theorems. In other words, if we just sort of throw out this field of mathematics, what is its sort of an arbitrary field of mathematics, what's its distribution of true theorems? Let's see. I'm talking here about sort of yeah, there's a lot of stuff here which has been kind of updated in the physicalization of mathematics, although nothing that the NKS book says isn't true. It's just there's a lot more to say now. I talk about this question of sort of how has mathematics expanded? How did mathematics choose its subject matter? And I kind of said in the NKS book, something which is kind of, again, much expanded in the physicalization of mathematics, which is that mathematics tends to be very much about, we got to have theorems that are true. There's like 3 million in the literature of mathematics to date. And so in a sense, the way that generalization tends to work in mathematics is to say, we got a theorem that's true, let's say unique factorization or something. Now let's puff out the axioms we're using to look at systems for which that same theorem is still true, but some other things are true as well. And so in a sense, mathematics is working by sort of progressive generalization while maintaining certain core true theorems. And that could be an argument, I said in NKS, for why mathematics manages to navigate through things where you're not dealing with undecidability, because it's always forcing itself to be talking about things about which theorems can be proved. A little bit like engineering typically doesn't deal with arbitrary computationally irreducible things, because we want to be able to say what's true. Okay, so this is another page that I've used many times. There's an updated version of it in the Physicalization of Metamathematics. This has to do with the question, well, let's say you're just enumerating true theorems, let's say in Boolean algebra. This is and or not Boolean algebra. The question is, which ones do we humans care about? Because most of these theorems are going to enumerate an infinite number of theorems, but most of them are just, okay, well, that's amusing, but we don't really care. So what I did in the NKS book was I said, let's take a textbook of logic, and they actually all have more or less the same conclusion in terms of this. And let's say, what are the theorems that people have given names to? You know, the law of excluded middle, De Morgan's laws, things like this, named laws of logic. And let's see how those are distributed in the space of all possible theorems about logic. So this highlights the ones that are given names in typical logic books. And what I noticed in this picture is something very surprising. I noticed that every theorem that was given a name in a logic book was one that was not provable from ones earlier in the list. And the definition of earlier in the list, which I sort of at first did quite arbitrarily, but then sort of tightened up a bit, is kind of a lexicographic ordering of sort of the raw complexity of these statements. Well, then we can say, given that, we can ask, which one of these is not provable from ones earlier in the list? And it turns out that every time there's one that, pretty much every time there's one that is given a name in logic textbooks, it has the property that it is not provable from things that are already in the list. Now, eventually, everything will be provable because we've managed to reproduce the axioms for Boolean algebra. But at the beginning, we don't have, if all we know is that A equals A and A, we don't know enough to have all the Boolean algebra. So we can't prove, we can, from A equals A and A, and we can't prove A equals A or A, and so that's a new theorem, so it's highlighted and it's given a name. But we can prove this theorem, we can't prove this theorem, and so on. So it's sort of a remarkable thing that we can get some indication, some empirical indication of which theorems are likely to be considered interesting by humans. And I've made quite a bit out of that in intervening years, of the possibility of sort of automatically determining in a giant search of all possible theorems. Imagine you type into Wolfram Alpha, here's a mathematical system I'm considering, now what's true from that? It will say, well, it could have some criterion for saying, well, these are theorems you might think are interesting. That was the concept there. So when you do this for NAND, it's much less obvious what's going on because we're much less familiar with kind of NAND theorems, and you can only really say what's interesting by kind of translation to things that we're used to. So let's see. Talking here about the network of theorems in mathematics. That's something that I explored again. I'll talk about that some more. Okay, so the basic point is that what I say here is that the conclusion is that computational irreducibility is rampant in mathematics. The principle of computational equivalence is alive and well in mathematics. The reason that it isn't so more obvious in working mathematics is because the strategies for sort of picking things in mathematics, like the strategies for picking things in engineering, are ones where you're kind of always at a place where you can foresee what's going on. That's the argument that I make here. And in a sense, in the physicalization of mathematics, I kind of generalize that argument to talk about observers in general. I think it's a stronger argument in the end. But in a sense, what I'm saying in the NKS book is that just like engineering systems haven't typically in the past shown great complexity because we humans pick ones where we can foresee what they'll do, so it is also with our mathematics. Okay, let's take a little bit of a look at the notes for this section. This is a section with a huge number of notes, and there's a lot of very, very juicy things in here. I'm going to go through these fairly quickly because But there's really, this is a heavily, very wonderful collection of notes here. So I'm talking about here about the concept of mathematics, and when people got the idea of sort of abstraction in mathematics, which is kind of the 1800s, of things like non-Euclidean geometry, abstract algebra, and so on. I talk here about history of models of mathematics is expanded upon more in the section on meta-modeling in the physicalization of mathematics. I talk about Leibniz, Frege, Peano, Russell, Whitehead, Post, all these people who thought that they had sort of a minimal model for what to represent mathematics in terms of. And it turned out that in the end, many of them, by the time we got to sort of the Turing machine story, many of them turned out to be equivalent. And that's part of the story of the principle of computational equivalence, that all these things turn out to be equivalent. And they turn out to be equivalent both between different models of computation and between these different models of mathematics. Okay, this is a more technical piece about axiom systems and how you apply axiom systems. This is to do with modus ponens versus replacement. This is again covered a little bit in more detail in the physicalization of mathematics, the new formalism for that. This is talking about the axioms for Boolean algebra and some of the history of different axiom systems for Boolean algebra. I'm going to talk here about all the different areas which I show in that big table of axiom systems as predicate logic, talk about arithmetic and the establishment of the Peano axioms, the simplified versions of the Peano axioms due to Raphael Robinson, in which there are things that can, in which there's more that can be proved, but things like x plus y equals y plus x can't be proved, Presburger arithmetic, where it is ultimately decidable, simplified form arithmetic, and so on. Talk about algebraic axioms, group theory axioms, semigroups, field theory, ring theory, other kinds of algebraic systems. Some of these would be nice examples to really try and look at in more detail now that we have more powerful theorem proving and Wolfram language and so on. Talk about real algebra, another example that has axiomatization, geometry. This is sort of a representation, a pictorial representation of Hilbert's axioms for geometry. This is something, again, studied in much more detail. In fact, in Wolfram language, where we have a whole array of capabilities now for synthetic geometry that's addressing this. Talking about category theory a little bit, and then talking about set theory. Typically, that's viewed as being sort of the fundamental axiom system for mathematics as mathematics is practiced today. It's a little bit of a mess, because whereas with arithmetic and integers, we have an intuitive sense of what we can expect integers to behave like. With infinite sets, we do not have that intuitive sense. And there are axioms of set theory where we can be confused about whether they're right or not. Like the continuum hypothesis is an axiom that we know is independent of all the other axioms of set theory. And there's a whole argument about whether it's true or not. In the physicalization of metamathematics, I argue that there is a definite answer to that question, at least for us humans as doers of mathematics. But that's a place where sort of that's the ultimate foundation of most current mathematics is attributed to set theory. Okay, talking about other axiom systems. This is details of, okay, this is structures of proofs and that kind of thing. That's very related in the end to kind of higher category theory, which talks about, in which you have these proofs, and then you have proofs between proofs and so on, something talked about elsewhere. This has to do with something which again is covered in the physicalization of metamathematics, about exactly how do you go from one expression to another? What kind of transformations can you make on symbolic expressions while maintaining their truthfulness or whatever, while having them be equivalent? Okay, axiom schemas, that's infinite collections of axiom systems. This is about proofs in practice and how complicated some of those have been, and the fact that Mathematica and Wolfram language makes it sort of less important to be able to say, and here's a proof. That sort of was important when the only way you could have a reproducible way of seeing what was true was to have a proof where other people could follow through and reproduce that proof. But now that we have Wolfram language and Mathematica, you can basically just say, look, the computer is going to run the same set of operations. And if our quality assurance and testing was correct, if it says this is the answer, then that's the answer. You don't need to write down a narrative proof that a human could read. And it may be very hard to do that. Okay, this is talking about tautologies with NANDs and the question of out of all possible NAND expressions, which ones correspond to tautologies. This is something which would actually be interesting to study in more detail here. Okay, this is talking about searching for proofs. This is talking about the equivalent of, this is essentially automated theorem proving. I think I talk here about automated theorem proving. This is what turned into find equational proof in Wolfram language. This is a little bit of the history of automated theorem proving. I realized after the fact that that proof of the axiom system for Boolean algebra that I did in the year 2000 was essentially remains the only unexpected result ever established with automated theorem proving. Most of what's been done with automated theorem proving is establishing things one sort of already knew were true from human proofs and so on. That was one case where one just went out into the computational universe and found something that's true with automated theorem proving and didn't know it was true. And I suppose that it's sort of ironic historically. Back in the 1970s, I was a big user of computer algebra and sort of became probably its biggest user as somebody who was not at the beginning a builder of systems to do that kind of thing. I later, by 1979, I was a builder of such systems, but I had previously been using them as a non-creator, using them to actually establish things. And the same thing happened with automated theorem proving back in 2000. And we added automated theorem proving to Wolfram language, but we're now working on more advanced ways to use those ideas through multi-computation. And I think the same pattern is going to repeat itself. Okay, this is talking about the concept of truth and falsity in formal systems, the negation operation that I talked about, talking a little bit about the history of Gödel's theorem, talking about the concept of essential incompleteness, whether something can be sort of, whether you can just put in axioms to make something complete and so on. It's a bit of a technical thing. Okay, this is about universality in the case of algebraic style axioms, again, a bit technical. This is talking about, okay, set theory and universality of set theory. I forgot all these notes. Wow, those are some cool notes. Somebody should lift these for Wikipedia and so on. There's a lot of interesting, clean stuff here that I think is probably not very well explained elsewhere. It took me a lot of effort to actually put these explicit forms that you can just sort of pick up and actually run and check and so on. Okay, this is some of the mechanics of that universal Diophantine equation. A lot of fun stuff about, the equation A equals mod B mod C. How can that be written in terms of pure arithmetic? And here's the answer: B equals A plus CD, and A is less than C. And you keep going, and it's like, how does prime Q get written in terms of pure arithmetic? And you have to sort of go through the sequence, like GCD is written as this sequence of equations, just pure integer equations. And it's kind of that's the chase to try and figure out, and that's what Gödel effectively had to do some pieces of to show that arithmetic is universal, that you can compile these operations that seem like they're logic and things like this into operations in arithmetic. And this is the bit XOR bit operations were some of the later ones that had to be established. Okay, talk about the fact that there are universal Diophantine equations that are known, but they're really complicated. Hilbert's 10th problem. Okay, this is another thing which was not really explored very well in the NKS book, is a sort of junior version of this Diophantine equation question, which is polynomial value sets. This is a good project somebody should look at. Again, it has to do with when is a polynomial positive? For what values of x and y is it positive? What is the positivity set, so to speak, in that system? And that's, again, a complicated thing. Okay, this is about statements in pure arithmetic. If you just start enumerating statements in pure arithmetic, which ones are true and how long are the proofs? Okay, this is no, this is not how long are the proofs. This is just showing that there are simple statements in pure arithmetic, like there are infinitely many primes of the form n squared plus 1. That's the statement in pure arithmetic, which you would have to prove using those operations, using those axioms. This shows what's actually true about the spacings between the values of n for which n squared plus 1 is prime. So in a sense, the complexity of this picture is a sign of the difficulty of proving this assertion in pure arithmetic. I talk about transfinite numbers. This is I looked at this note recently. It's a rather nice note on transfinite numbers. Transfinite numbers may finally get a use in Wolfram language in talking about infinite lists real soon. This is talking about growth rates of functions and growths that could be transfinite in size. This is actually relevant to stuff we're working on right now. This is an example. Gödel had this statement is unprovable as an example of an unprovable statement in arithmetic. A chap called Ruben Goodstein, who was a student of Wittgenstein's, found a slightly simpler case, and this is a nice concrete version of these Goodstein sequences, saying that if this particular recurrence, Wolfram language recurrence, always terminates, then then that's a statement that's unprovable in pure arithmetic. And one can see that while these three always terminate, this one here, G4, takes 10 to this huge power number of steps to terminate. And as you go further, it's even an outrageously larger number of steps that it will take to terminate. This is about encodings of arithmetic for universality proofs. This is about specific Diophantine equations and what's known about different kinds of Diophantine equations. It's kind of like a, again, there's a lot of really good, juicy, pithy stuff here. If I want to know about Diophantine equations and what's known, I look in the notes to the NKS book, not somewhere else. At least it should be on MathWorld. Perhaps it is on MathWorld. There probably are quotes from this on MathWorld now. There should be. In any case, the thing that's sort of interesting here is that equations like quadratic equations, it was known in antiquity how to linear equations were known how to solve in antiquity. Diophantus himself did that. Then it took up to Gauss in the 1800s to do quadratic Diophantine equations. And then early 1900s, we get to elliptic ones, which involve some cubes and so on. And it's kind of like a very slow process, which in fact will probably terminate in the sense that there will be a point at which we have to say, no, we can't go any further. There's undecidability at this level. We don't yet know where that is. Okay, this is particular Diophantine equations I'm talking about to give examples of different kinds of things that happen. Oh, those are the ones on that page where I'm enumerating solutions. Those are properties of those Diophantine equations. Okay, this is, oh boy, I forgot this page is here. These are examples of other Diophantine equations that I found that have very large solutions. This would be another good project to repeat this nowadays and find some other examples of this kind of thing. Of Diophantine equations that are small equations, but where the minimal solutions are large. Okay, this is an example of something related to Diophantine equations about nearby powers. Just another one of these things where it's really hard to know. It's something about integers. It's very hard to know what's true. These are unsolved problems in number theory that still remain unsolved after 20 years have gone by. Some of them have been unsolved for a couple of thousand years. But this is just a list of such unsolved problems. And the question is, will it turn out that the Peano axioms are just too weak to reach any of these? Could be that they're all undecidable from the current axioms of arithmetic. Fermat's last theorem, I talk about that had fairly recently been proved, although it had been hanging out there for a few hundred years. It's talking about adding axiom systems, axioms to mathematics. That's okay. And this is higher order logic. this is a complicated note, which I come back to with repeatedly, which is about the concept of truth and incompleteness and the question of statements that are sort of by default true. So, for example, the Riemann hypothesis is something which, if you show that it is undecidable whether it is true, then it is necessarily true. And so there's sort of this whole question about when are their default truth values. This note is a pretty clean discussion of that. Okay, this is actually a list. I'd mentioned that mathematics sort of grows by generalizing things that were already established as true. This is kind of a nice list of the sequence of things from Grassmann algebra to axiomatic real numbers to transfinite ordinals and so on that were sort of, this is the tower starting with positive integers before 10,000 BC and climbing up to surreal numbers and so on in the 1970s. This is the sort of tower of generalization. Again, it would be nice to see this more explicitly. And now that we have in the physicalization of mathematics piece, I talk about that in a little bit more detail. Although it'd be nice to see this complete sequence shown in explicit terms in terms of definitions. More detail about the cellular automaton axioms. This is about theorems, proofs about practical programs. Is a place where it's of great interest to try and use theorem proving techniques, although they haven't been used that successfully yet. We're interested in using them for our compiler, for example. Okay, consistency. Those are example multi-way systems about non-standard arithmetic where the Peano axioms are true, but they're not like the operation. Things don't look like ordinary integers. I told you there are a lot of notes in this section. This is about multi-way systems and their relationship to algebraic axioms, something that's again explored more in the physicalization of mathematics. Truth tables, okay, proofs of these axiom systems. Okay, this is showing whether an axiom system is really an axiom system for what you think it's an axiom system for. This is again something different. This is junctional calculus for conjunctions. This is again something where it would be nice to try and establish a minimal axiom system. I was not able to do that in working on the NKS book. In this case, again, I was not able to establish a minimum maximum system. That's something, again, one should try to do now that we have faster, more powerful computers and better theorem proving technology. Implicational calculus, same story. I got to some minimal candidates, but was not able to ultimately nail it. Okay, this is, let's see. Yeah, this is more algebraic systems. Again, it will be interesting for all of these algebraic systems to look for minimal axiom systems for them. And also these algebraic systems, I hope that they're now all in the axiomatic system function of Wolfram language. Things like squags and central semi-groupoids and so on. Okay, this is talking about the relationship between combinators and axiomatic systems. This is talking about forcing of operators. Let's not go into that. I mentioned model theory earlier. Okay, this is actually an interesting note, which I forgot existed, about the relationship between multi-way systems and operator systems. This again is covered in a different way in the physicalization of mathematics, where more of its significance is highlighted. This is talking about, this is an amusing question. We have words for and or not in English. Are there words where there's a word for NAND, for example? There's words for XOR in some languages, Latin and Finnish apparently. Well, Latin I know has that word, distinguishes exclusive OR from inclusive OR, apparently so does Finnish. And there's a question of whether NAND is a word in any human language. And I think the answer is no, although circuit designers routinely do talk in terms of NANDs. But this is sort of a fun question, actually, will be, again, worth looking at again. now that we have more extensive dictionaries and so on in Wolfram language and such like, about this question of about for what are there, how do you actually construct, we think of NAND as not being something we normally think in terms of, and that's reflected in the fact that human languages don't have words for NAND. Okay, these are the very confusing many different notations. This is a great summary page. The many different notations that one can use for things like equality, from gates to ease to triple bars and so on. This is about functional completeness. Somewhat amusingly, my son Christopher studied this question, I don't know, 6-7 years ago, and got a bunch of results on it. And the results seem to be nowhere to be found on the web, except in this note in the back of the NKS book. And his study of this particular thing was utterly independent of my interest in this area. And it's one of those apples and trees type stories that the one place, I mean, he did a much more complete study of this, and with many other results. But the one place where there was some definite thing that was said was in the notes of the NKS book. Okay, this is part of the big hunt for the minimal axiom system for Boolean algebra. I covered this in much more detail in the post that I wrote back in 2018 about logic and understandability. But this was what I talked about in the NKS book. Let's see, this is more stuff about that. The history, I talked about that history in more detail in the post, along with some of the human stories of some of the people involved. In the NKS book, I didn't do any of those human story discussions. Okay, this is more about theorems in, okay, there's multi-valued logic. Okay, so here's a question. When you use that axiom system for Boolean algebra, my minimal axiom system for Boolean algebra, is it just a really inefficient axiom system to use? That is, if you just look at how long does it take to prove various statements in Boolean algebra, is it much faster to prove it with other axiom systems? And what we see here is the lengths of the proofs of the first 500 or so statements of Boolean algebra proved with different axiom systems. And what you see is that the minimal axiom systems of mine, this is another axiom system of mine actually that involves also having an explicit commutativity axiom, but the minimal axiom systems of mine, look, they're pretty inefficient. They take 120 steps to prove anything. But it turns out they're taking those 120 steps to basically prove one lemma, and that lemma is commutativity. Once they've proved that, they're cooking along, and then they prove things in 40 steps and so on. They're very competitive with the best axiom systems down here at proving things. So in other words, there's one thing you have to cache, and then you don't lose anything by having a more minimal basis for computation. That's an important general principle, that this idea that something like Rule 110, for example, you might say it's an incredibly inefficient computer. But no, once you've got a compiler, you can probably make perfectly efficient computation on it. And that's important when you think about, I don't know, making things in terms of molecules. It's like, well, there's a big stack of compiler, but once you've got that, then you're really able to be efficient, even if the foundations are much simpler than you thought. Okay, let's see. Other more technical notes. Okay, this is a section on empirical metamathematics. It's sort of funny in a way, because this section, I looked at the empirical mathematics. That is, if you look at actual theorems that people prove, the sort of geography of mathematics, of where in mathematical space people choose to populate, you can ask questions like, what's the signature of an easy theorem, a powerful theorem, things like that, in this network of all possible proofs? By the way, this is something that should be explored more, but down at the bottom here, I decided I would take the axiom system, the axioms that the theorems that Euclid had established in his books. So I think there are 10 axioms and 465 theorems that appear in those books. And I would look at what the network of how one axiom leads to another is. How one theorem leads to another. This is the dependency network of Euclid. And so I said here, the longest to prove thing is the result that takes 30-something steps from the axioms, and it's the result that there are 5 Platonic solids. Now, this idea of empirical metamathematics, I wrote a very long, it's like 70-page long expansion of that one part of one note of the NKS book. In fact, I show the note here. There it is. And this post is a giant expansion of that note that shows, there's more about theorem distributions. This shows in detail how that theorem distribution really comes to be and how you really get from the axioms up here down to the results down here that there are 5 Platonic solids. And so that one note in the NKS book, and this is just an example, and the NKS book is absolutely full of these kinds of seeds of things that can be studied from it. And that was one example where that little piece there turned into a 70-page document. And even then, there's much more to say about that topic. Talking about the different styles of different foundational frameworks for mathematics people have discussed. Invention versus discovery. Well, I have more to say about that in the physicalization of mathematics. Talk about the relationship between brains and mathematics, and how mathematicians think about mathematics, and whether the mathematics we have is a consequence of the way our brains are built. And there's more to say about that in the physicalization of mathematics again. That's actually interesting and probably should be looked at again in the context of the physicalization of mathematics. This is about different kinds of structures for establishing things in mathematics. Okay, that was the section on mathematics. As you could see, it was a long and complex section, and it was one that has now been the seed. Much of that section has now been sort of worked over in, I went to the wrong chapter. Much of that section has now been worked over in the physicalization of mathematics, which really goes a lot further. The physicalization of mathematics is to this section as the physics project, in some sense, is to chapter 9. And so it's a much more detailed exploration. Okay, let's turn to the next section. It's called Intelligence in the Universe. And what is this very different application of the principle of computational equivalence? I start up by saying whether or not we as humans are the only examples of intelligence in the universe is one of the great unanswered questions of science. And I then go and talk about this question of whether the weather has a mind of its own. And the idea that the principle of computational equivalence says that the fluid dynamics of the weather should in fact be something that has the same computational richness as Rule 110 or as our brains, so that in some sense it's true that the weather has a mind of its own. Now, I should say that this section, its main conclusion is that there's minds all over the place, that all of these computational systems can act like minds. And in a sense, but I discuss that in a little bit more detail because there's more that one thinks of about minds. But I will say that this section was what led to Wolfram Alpha, because I had been thinking about making a computational knowledge engine kind of idea, not with that term, but taking knowledge and making it computational. I've been thinking about that since I was a kid. And I'd always thought, well, gosh, we'd have to build sort of a general AI to be able to make use of general knowledge in a computational way. But this section convinced me that if the principle of computational equivalence is true, then there is no bright line for intelligence. Everything is merely computational. And that means we should be able to build a Wolfram Alpha. And I suppose I could view the existence of Wolfram Alpha as another piece of evidence for the principle of computational equivalence, another piece of evidence for the intuition that everything is merely computational. There's not this bucket of special computation that might be sort of computation with intelligence as opposed to just computation. Well, so I talk about what intelligence might be and the definition of it, and learning and adaptation and abstraction and so on, and talk about how that can be interpreted in terms of physical processes and so on. I talk about the definition of life here as well. I talk a little bit about, this idea that, first of all, people said when things can move themselves, then they must be alive. And then you had steam engines. People then said when things can reproduce themselves, then they must be alive. but it turns out this is an example of a cellular automaton. That's a really simple cellular automaton that successfully reproduces, in this case, an arbitrary initial configuration, but there are other cases where you can reproduce just specific initial configurations. Self-reproduction is something that can happen in all sorts of systems. It's not specific to life as we see it in life on Earth. And of course, life on Earth has this feature that it all comes from a common lineage. It all has RNA, it all has cell membranes. It's all sort of historically related. And this question of what's the more general definition of life is an interesting one. I talk about the fact that there may be no bright line there, as there is no bright line in, I argue, in the notion of intelligence. So I then talk about this question about, this is this question about whether under if there is intelligence, sort of, can you communicate with it? And the relationship between intelligence and meaning, there's sort of these terms: intelligence, meaning, purpose. And so the question is, when there is a thing that does something, does it mean something? Does it have a purpose in doing that thing? And I talk a bit about this. I've written about this at some length, actually, elsewhere. I wrote a big piece. I mean, that's, boy, I better not be thinking that I'm mining NKS for the rest of my life, but no, there's plenty of, but NKS is an incredibly rich source of both results and questions. I wrote a big piece about, that's nominally different, about sort of what counts as, how can you tell when something is meaningful, and and sort of the interpretation of meaning and so on. That's a picture from the NKS book, actually. That's a colorized version of a picture from the, but not colorized. It's the original color version of a picture from the NKS book. But anyway, so the question is, how do you tell whether something was created for a purpose? How do you tell if something is an intentional artifact versus a thing that is merely doing what it does? You see Rule 30 somewhere. Was it created as Rule 30, or is it just doing what Rule 30 does? So one of the things that I talked about, I say here, I've forgotten the section actually, but I said here, cellular automata whose behavior does and does not give the impression of being purposeful. That one sort of gives the impression of being purposeful, and that one does not. And okay, what does it mean to give the impression of being purposeful? And I say here, if the purpose is to generate a uniformly expanding pattern, it seems more plausible that the top cellular automaton should have been the one created for that purpose. So given a purpose that you define, you can ask the question, find a system that, if you look at a system, is the system that you've got somehow minimal for achieving that purpose? If you define a purpose, is the system you're looking at minimal for that purpose or not? And so this is a cellular automaton that achieves the purpose of doubling the initial line of black cells here. So in each case, there's n black cells, and there's 2n in the input and 2n in the output. Okay, so now we look at all these pictures. These are all cellular automata that achieve the purpose of doubling the initial conditions. But there are ones that do it in a very elaborate way. And we could ask the question, if we were to see these, if we were to discover these, we were to dig them up somewhere, and we knew somehow, we said, there is a purpose, it's the doubling purpose. It's not clear how we know that, but let's say we know that. Then we could say, well, which of these was plausibly made for that purpose, and which of them are just full of ornamental crud that has nothing to do with that purpose? And so we might say, well, the one that's sort of minimal for the purpose is the one that we can say was constructed for a purpose. Now, an interesting question is, what happens if we apply that to human engineering? Well, it's sort of embarrassing, because most engineering that we do is not minimal for its purpose. It was constructed that way because of the history of actual human engineering, that we knew we could make cogs and levers and so on. We built up in that narrative to create the thing we created. And it's certainly not minimal for that purpose. Just as Boolean algebra, what we found that people had constructed axiom systems for Boolean algebra, but they were not minimal for that purpose. We found the one that was minimal. Okay, so I talk a bit about extraterrestrial intelligence and the question of with advanced technology, you can like move stars around. And the question is, if you could move stars around, in what pattern would you move the stars to give evidence of purpose? Not obvious what the answer to that is. What would be a message that we could receive that would give evidence of purpose? Well, what we realize is that it's a complicated story, and there really isn't a correct answer to this question. I talk about the fact that what we consider to be noise, somebody else might consider to be a meaningful message. When we say, let's look at that pulsar magnetosphere, it's producing this very elaborate pattern of radio signals. Is that an example of intelligence or not? We say, no, it's just a pulsar magnetosphere. But to the pulsar magnetosphere, looking at us, it's, oh, that's just a bunch of carbon, nitrogen, oxygen reactions going on. Well, hydrogen, whatever, reactions going on. So this question of where, and as a practical matter, when people in the past, and I talk about this in the notes to the NKS book, had tried to see, well, let's talk about that when we come to the notes, the examples of sort of how extraterrestrials might have been, what people thought of as examples of that. And so anyway, what I'm saying here is basically that, gosh, there's a longer section than I remember, that whenever we see sort of sophisticated computation going on in the universe, we can't really distinguish that from intelligence. We can say that it is not connected to purposes that we know. In modern terms, it is some distance away in rulal space. But as I say here, it's impossible to know without detailed cultural background whether the thing that we're looking at is purposeful art and so on. I talk about that in much more detail in this piece that I wrote about showing off to the universe beacons for the afterlife of our civilization. And I hope somebody is putting some of these in chat, the links to these pieces for people's interest. That was trying to answer the very practical question of, if you are going to put an object on a spacecraft, and you're going to put it, you're going to have it go out of the solar system out into the into interstellar space. What can you put on that people could understand, and why that's a sort of philosophically doomed question. And I talk here about this question of whether there is, in a sense, in rulal space, what's the density of understandable to us stuff going on in what I now call rulal space would be. I talk about class 4 cellular automata as kind of an example of something where we can kind of see what's going on, where we have a narrative to discuss something. Let's see. This is really talking about let's see. Okay, that's so I'm talking here about sort of the resolution of kind of the paradox of why we don't see extraterrestrial intelligence is, well, actually we do. Any computational, almost all these systems, according to the principle of computational equivalence, are capable of sophisticated computation. That is extraterrestrial intelligence. It's just that it is not intelligence which is aligned with ours in terms of what we sort of understand at a narrative level its purpose to be. And that's something that we can tighten up a lot in talking about the Ruliad and rulal space and so on, but that's the basic conclusion already in the NKS book. Okay, let's have a quick look at some notes for this section. There are lots of fun notes in this section. Oh boy. See, as I was getting towards the end of the book, I think it became very note heavy. Okay, this is, let's go through these. Animism. That sort of has a lot of resonance with what we're talking about. I talk about the weather and what's actually involved in the dynamics of the weather and fluid dynamics and its unpredictability, and the computational irreducibility of the weather. Don't even start on climate. The weather is the local version of that, and the story of computational irreducibility there. I talk about the definition of intelligence and people's rather unsatisfactory efforts to things like define the general intelligence factor G that you could test in IQ tests and so on, and why that's sort of a doomed idea. I talk about defining life and the history of that effort. I have to say, I always repeat the story when I was a kid and the first spacecraft landed on Mars and they wanted to test, is there life there? And people said, well, what's the definition of life? And eventually it was, well, you feed sugar to the soil that might have microbes in it, and you see if it metabolizes. But clearly, that's a very specific, very human very terrestrial terrestrial biology definition of what life is. And one would like to know something more abstract. I talk a little bit here about the origin of life. And that's something that we're actually studying a bit more with our subchemistry thing that's emerged from the physics project and the mathematics project. Talk about specific examples of self-reproduction, talk about the extraterrestrial life and microorganisms. Okay. The sentence is like, the overall morphology of living systems on Earth seems to be greatly affected by their basically gelatinous character. So even systems based on solids or gases would likely not be recognized by us as life, I say, in terms of just sort of the science fiction thing of, you go to the weird planet and is there something alive there? Okay, the history of extraterrestrial life. I talk about people's belief in, well, talk about UFOs and other such things, and the sort of history. There's a brief, again, I'm rather pleased with these sort of pithy histories of things, of kind of thinking about extraterrestrial life. This is talking more about intelligence. Are bird songs intelligent? Is the fact that you can go find the actual neurons in the bird's brain that produce these things, is that a sign it's not an example of something like intelligence? Well, you could no doubt do that eventually with humans. I talk about whale songs, talked about this again in that piece about beacons for the afterlife of our civilization. Animal communication, more on this question of meaning. Talk about sort of general theories of communication. Actually, I should reread this note. I talk about the Sapir-Whorf hypothesis. That was a key element in that movie Arrival that we did some work with. I think it's also something where, as even though the linguist who helped with that movie didn't really believe in the idea, the Sapir-Whorf hypothesis, that the definition of a language sort of affects how you can think about things. As a designer of computational languages, I can say that I'm really quite certain from huge amounts of evidence that the design of the language is important in how people think about things. I talk about mathematical notation as an example of language. And I talk about that sort of what we think we're generalizing with our computational language. And this is communication between computers, meaning in programs. Let's see. Actually, this is an interesting note that I should reread. Yeah, that's interesting. Well, that's an interesting note. I should pin that for rereading. Okay. This is a question of when you see an artifact, how do you know it's an artifact? I have my glass of water here, and he says, making use of this artifact. How do I know it's an artifact? Well, you know what? It has this very simple form. It's round at the top and things like that. It's round, and that's kind of a clue that it's an artifact. And what's interesting here, I tried to catalog, and this would be a fun thing to do in more detail. I tried to catalog the different forms of objects, from arrowheads to boomerangs to propellers and so on, the different morphologies of artifacts that people have invented. And I comment on the fact that they're not terribly complicated. Slowly, there are more sophisticated things, like there are some acoustic absorbers, which are in quadratic residue sequences. They look a bit more complicated. And actually, in the 20 years since this time, through NKS work, people have ended up generating some more complicated forms, some more complicated morphologies that are used for engineered artifacts, so to speak. This is about recognizing artifacts, and this is related to extraterrestrial intelligence and so on. There's just a lot of weird stuff in here. Lenticular clouds are sometimes mistaken for UFOs, I say. The cuboid in 2001, the fact that it was an exact cuboid was intended to suggest it was an artifact. I talk about that actually in detail in a piece that I wrote about the movie 2001 that must have been in 2018. So this question about recognizing artifacts, and this was every one of these notes, there's a lot more research that went into these than is obvious from the few sentences that are said here. This was the result of talking to some archaeologists and so on, and trying to understand this question of how do you tell whether a bunch of stones laid out in a certain way were put there for a purpose or not? And I talk about that again in that other piece I wrote. Artifacts in data, well, that's become a thing that's sort of is that data fraudulent type thing. Artifacts made by animals, whether there could be meaning in molecular biology, is there a message written in our DNA, so to speak? What would that even mean? Decompilation, going from machine code to a higher level description, that's sort of can one find meaning out of this collection of bits? Archaeology, the question of whether we can sort of make a thread of meaning that connects us to history and archaeology. Similarly, dead languages. Is there a chain of language that goes back to some language from the past that allows us to understand meaning from that language? Okay, this is a more philosophical piece about teleology and the question of how do you distinguish whether something is doing what it's doing for a purpose or just doing what it's doing because that's what it does. And I talk here about the sort of the history of that kind of philosophy. Okay, this is the doubling cellular automaton and more doubling cellular automata. Okay, this is yet another thing that was relegated to the notes, but it's quite an interesting thing, probably should have further study. This is the question of what's the simplest cellular automaton that generates as its center column sequence some particular thing, and some particular periodic sequence, and how far do you have to go before you get a cellular automaton that generates sort of all possible, before you get to cellular automata that can generate all possible, no, this is just black with a bunch of white cells. How do you get black with 12 white cells after it? Well, this is the simplest rule that does that, and so on. Sort of a way of finding, if you have the purpose of generating a black cell and a run of n white cells, what's the minimal rule that gets you to that? Okay, minimal theories. Oh boy, more intelligence in the universe. I talk about much of this again in that Beacons for the Afterlife of Our Civilization. This is Earth from space. What do you see? This was the result of talking to some astronauts and asking them, when you look at the Earth, what kinds of things do you see that are that suggest that there was, that there's sort of intelligence and intentionality on the Earth? And there was a fun story here I do have to tell. We one of the things that you see, according to astronauts I talked to, is this circle in New Zealand. And this was before the web. We were doing this research, and we contacted the Geological Survey in New Zealand and about this, what was this circular object there, and so on. And they sent back something saying, just if you're writing a geology textbook, just don't say it's the volcano. It's a park that happens to be perfectly circular, and there are sheep that graze inside the park but not outside, or the other way around, and that's what causes the apparent circle. But was a lot of fun stuff. It would be, again, something that would be interesting to look at again with more data on, for example, lights at night. This was a thing where I found the sort of the longest straight sequence of lights at night, the longest straight road is somewhere in Australia. The longest sequence of lights at night is across Kazakhstan, apparently. That was a railroad that was built straight. And so it's something where you look at it from space, it's like, well, there's all these borders of continents and things. Those are just geological, but oh, there's this straight sequence of lights. You know, that doesn't look very geological. It's not a, you know, there's no lava being produced that's like that, maybe. Okay, this is about astronomical phenomena. Oh boy, radio emissions. And this is the story I was alluding to earlier about the pulsar magnetosphere and is it intelligent or not. Back in the day, people were looking, actually, I think I talk about this maybe in another note here. I'm talking about the different radio signals produced by the Earth and natural radio emissions, things like in the ionosphere, things in astrophysics. I talk about artificial radio signals, and this is a little bit out of date now because there's more to say. In fact, even in an obituary I wrote for a person called Sol Golom, who was involved in inventing a bunch of the mathematics behind cellular telephony, I talk more about this. But basically, this is the question of, if you look at the actual radio emissions from the Earth, how regular are they? And the more we manage to pack in information and the more we manage to spread out over the spectrum, the less regular they're going to look. So very early radio had a very clear carrier frequency, very clear, very clear single frequency signal. And for example, a lot of the experiments that are done on search for extraterrestrial intelligence, they concentrate on that early radio idea of a single carrier frequency. But increasingly, and when we go to 5G and 6G and so on, the whole idea of those things is don't just broadcast, this one frequency all the way out into space. Instead, have things which are much more local, much more phased arrays, things like this, and pack the data in and don't make it something where there's a recognizable wasteful carrier. So in a sense, the future of radio communication is a future where you can't tell that it's something other than random. And in fact, random is sort of the best. It's the one that has the most Shannon information packed into it. And that's what we're going to. And this talks about that, that trend. It's talking about the most intense artificial radio emission right now from the Earth is the 50 or 60 hertz hum from power lines. Most intense directed signals are from radars used for ballistic missile detection. Okay, so this is talking about the history of SETI. Actually, this is a fun story from Tesla and Marconi, who were noticed that I think Marconi noticed it in his yacht going in the middle of the Atlantic, that he got these radio signals which were making these, funny woo 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 type sounds. And he didn't think this, but Tesla said that must be signals from the Martians signaling us with radio. It turns out, although the things sound a lot like whale songs, they're actually modes of the ionosphere, and it's a pure magnetohydrodynamical physical phenomenon. There's a long story here. I'd actually forgotten this one. Jansky, 1931, noticed radio emission from the galaxy. It seemed too random to be intelligent, but then people kind of, I remember these folks actually evangelizing this idea of using radio telescopes to search for sort of radio signals that might be of intelligent origin. Let's see. So I'm talking about, I think I talk here, there's just a lot of fun notes in here about detection methods for SETI. Yeah, well, eventually people will pay attention to this. it's not good enough to just look for these sort of single frequency carrier waves, but it's not really good enough to look for anything, because in a sense, the full story is a story of kind of intelligence everywhere. Messages to send to extraterrestrials. I just saw an example of this just yesterday that was like, boy, people make the most elementary mistakes. People don't understand that the way we think about things is incredibly specific to us. But there's a long history to, which I talk about in much more detail in that Beacons for the Afterlife of Our Civilization piece, of what to send to sort of indicate, give evidence of intelligence, so to speak. I think Gauss had a nice suggestion, which was to cut down a clearing in the Siberian forests in the shape of the typical proof of the Pythagorean theorem. That's kind of at least a nice one. Okay, I talk here about, again, you never know what you're going to find in the notes to the NKS book. I talk here about extraterrestrials in science fiction, and different kinds of different kinds of things there, and all sorts of weird cases of one-of-a-kind beings and other things like that. Okay, this is about practical arguments about the lack of extraterrestrials that we can see. This is kind of the flip side of a list that I made actually for sort of backstory for the Arrival movie that I talk about in a post that I wrote about that. But there's sort of some fun stuff here. Although in the end, I say out of 6 billion humans, it's notable that only extremely few choose, say, to explore life in the depths of the ocean. Of course, that number of 6 billion is now wrong 20 years later. Okay, so I'm gonna talk about the 2 more sections here, and I can't believe this is. I thought, boy, breaking chapter 12 up into 2 sections, two times would be enough, but there's just a lot here. I think the end of the NKS book was just really rich. This is about implications for technology and the idea that instead of just constructing technology from scratch, one can kind of search the computational universe and mine technology from the computational universe. And that's a powerful way to get technology. And indeed, it's one that we've made a great deal of use of in the last couple of decades or more in building Wolfram language. It's something which, in a very much more complicated form, has also been used in the whole deep learning neural net idea. But that's something that where there's a much clearer version of that one can do purely on the basis of NKS. And I think that's what will eventually be the story. But now we're dealing with these neural nets, which are much more tweakable with millions of parameters and so on, rather than the kind of thing we see in NKS, where there are programs with very small numbers of small sets of rules. Let's see. I say here in this note that I'm not going to talk a great deal about technology. I talk here about the applications of randomness, which is one type of thing like Rule 30. Where can you use the fact that it's easy to make randomness? And the answer is lots of places. I talk about self-assembly. Actually, we're doing a bunch more work on that in connection with subchemistry, nanotechnology. Also, the idea of taking the sort of traditional idea of taking a structure we know works on a large scale and just shrinking it down. That's the sort of traditional nanotechnology. The one that's more based on NKS says you take the things that are simple components and you kind of expand that up by seeing what can those components be made to do. And I think that's a powerful way to do it. This is talking about searching for technology. It's talking about, light bulbs from Edison, chemotherapy substances in the early 1900s, things like this. There's a small history of this sort of just search for technology. You know what your purpose is, now just do a search. We've really developed that a lot more extensively, and it's also something that's come about in deep learning and neural nets and so on, to just say, once you know what the purpose is, then if you can define the purpose, if you can have a computational language to define the purpose, then just go search out in the computational universe for the thing to get to find that the thing which minimally achieves that purpose. Now, I talk here about implications for chemistry. We're back thinking about chemistry again now. I talk about automated theorem proving in chemistry. That's something very much related to our subchemistry discussion. I talk about the question, just as we were talking about in mathematics, what are the interesting theorems out of all possible theorems? And I say, what are the interesting chemicals out of all possible chemicals? And we went and looked up in the chemical literature at the time, what fraction of all chemicals of a given structure were actually listed, and up to size 10, they were all listed, and then they stopped being listed. And here's a picture that shows this is something we can now do very nicely in Wolfram language. This is something which asks the question, how computationally irreducible is chemistry? To what extent can you, given sort of given a fact about a molecule, like what its structure is, how can you conclude things about it? Well, it turns out the boiling points of things like alkanes, hydrocarbons like that, there's a pretty decent empirical formula for boiling points. But when it comes to melting points, what you're dealing with is asking whether these weird shaped molecules fit together in sort of puzzle pieces into a solid. And that's something very much like the tiling problems that we talked about back in chapter 5, and that has all kinds of undecidability questions. And as a practical matter, that means that it's very hard to know where the melting points will be. And sometimes it's when you have a physical material, it never really forms a nice crystalline solid. It forms a big blob of tar or something. This is things mined for technology. This is talking about future technology. This is an interesting topic I've written about at some length elsewhere, how technology determines the things we do. The things we do determine what purposes we think are worth doing, and those then feed back into the technology. And that's kind of a cycle that occurs there. Okay, I have another section here, and I'm kind of wondering whether perhaps I should move this to a different day, because I think that we've got a section here about the historical perspective. It's only 3 pages long, but it has, should I do this now, or should I postpone it for another day and cover this? I think maybe we'll move it to next week, and next week we'll talk about the very end of the NKS book, and the kind of the interesting sort of story going from the first sentence of the NKS book to the last sentence of the NKS book and everything in between, and talking about kind of the historical perspectives and some of the meta discussion that I have in the NKS book. So I think we should wrap for now. And as a matter of fact, I have another live stream coming up for my day job in minus some number of minutes here, but I would like to remind you, this is we've been talking about the story of things that are in the big book. You know, I got to be better at showing the big book here. There we go. Getting ready for its 20th anniversary on May 14th. And as I say, we'll have another one of these sessions next Monday, covering the very, very last subsection of the NKS book and some of its meta information. And I look forward to talking to you again then.